Imagine a particle so small it can slip through the walls of a living cell, yet so durable it will outlast the building you're standing in. These are nanoplastics, particles smaller than 50 nanometers that have become an invisible part of our global water cycle. For years, filtering these has been a mechanical nightmare. Traditional meshes fine enough to catch them require massive amounts of energy to push water through, and they clog almost instantly, rendering the hardware useless. But in February 2026, researchers at Tsinghua University revealed a breakthrough, a filtration system that doesn't just catch these ghosts, it powers itself using the very water it's cleaning. The secret isn't just a better mesh, it's a fundamental shift in how we use physics. Instead of relying on external power grids, this system harvests energy from the friction of flowing water. This is the world of the Tribal Electric Nanogenerator, or TENG. It's a piece of mechanical engineering that turns a simple plumbing fixture into a high-voltage power plant at the microscale. By the time we're done today, you'll see how this device uses material science to turn the ocean's greatest threat into its own solution. To understand why this is a game changer, we have to look at the scale. A nanoplastic particle is to a grain of sand what a grain of sand is to a skyscraper. They are essentially invisible to mechanical filters, but the Tsinghua team didn't try to build a smaller hole. They built an electric trap, and the engineering behind that trap starts with the very movement of the water itself. It's a beautiful marriage of fluid dynamics and electrostatics. Let's dive into the first layer, the friction engine. The triboelectric effect is something you've experienced every time you felt a static shock from a doorknob. It's the transfer of electrons between two materials when they come into contact. In this filter, the doorknob is a metallic filter coated in a specialized polymer, and the hand is the flowing water. As the water rushes past, it strips and deposits electrons, creating a constant charge. This isn't just a tiny spark. The mechanical design of the tang allows it to amplify this friction into a high-voltage field that can reach thousands of volts, all without a single battery. But having power is only half the battle. You need a way to use that power to actually grab particles that are effectively weightless in the water flow. This brings us to the second pillar of this technology, the material science of the magnesium oxide and polymer-coated metallic filter. This is where the trap is physically built, and the engineering here happens at the atomic level. The physics of the TANG system is a masterclass in efficiency. It uses a sliding mode triboelectric generator where the lateral motion of water creates constant contact and separation cycles. Each time the water moves, it creates a potential difference. The clever part? The engineers used a multi-layered zigzag architecture to maximize the surface area in a tiny volume. This allows the system to generate enough voltage to create a powerful electrostatic field across the entire filter, turning the whole device into a giant magnet for plastic. Now let's talk about the magnesium oxide coating. MgO is a fascinating material because it possesses a high dielectric constant and a specific surface chemistry that loves to bond with polymers. By coating the metallic filter with MgO, the engineers created a surface that doesn't just wait for plastic to hit it, it actively pulls the plastic out of the water stream through polar attraction. This is how they capture particles smaller than 50 nanometers, sizes that would pass through even the most advanced conventional membranes. But there's a problem. If you just keep catching plastic, the filter eventually fills up. In a normal system, this is where the filter dies and ends up in a landfill. The Tsinghua team solved this with a reverse field mechanical process. By using the stored energy from the tang, they can actually flip the switch on the physics. Instead of an attractive force, the filter suddenly generates a repulsive force. It literally pushes the captured plastic off its surface and back into a concentrated waste stream. This flushing process is purely mechanical and electrical. No chemicals are needed, and no high-pressure backwashing is required. It's clean, elegant, and incredibly efficient. Because the MgO and polymer coating is so durable, the hardware can survive this reset over and over again. Testing shows it maintains its efficiency for over 20 full cycles. In the world of nanotech, 20 cycles is an eternity. It transforms the filter from a consumable to a piece of long-term infrastructure. Think of it like a reusable lint roller for the ocean. But instead of sticky tape, it uses the fundamental forces of the universe to keep itself clean. This self-powered nature means these filters can be deployed in places where there is no power grid, remote rivers, developing villages, or even deep-sea monitoring stations. The engineering isn't just clever, it's democratic. It brings high-end nanotech to the places that need it most. So, what does the future look like when we can finally filter the unfilterable? It starts with the hardware scaling up from the lab to the real world. By 2027, we could see these integrated into every wastewater treatment plant, catching nanoplastics before they ever reach the ocean. But the real potential lies in the modularity of the design. Because it's self-powered, you can stack these units like Lego bricks to handle any volume of water. The mechanical process of the reverse field reset is what makes this economically viable. Without it, the cost of replacing specialized MgO filters would be astronomical. Instead, the only input is the kinetic energy of the water itself. It's a closed-loop system where the problem, water pollution, provides the energy for its own solution. This is the genius part engineers strive for, a design where the constraints of the environment become the drivers of the mechanism. As we look toward the 2030s, this technology could even be miniaturized for personal use. Imagine a water bottle that cleans nanoplastics as you pour, powered simply by the motion of the water. Or industrial cooling systems that prevent plastic buildup in sensitive machinery, extending the life of our global infrastructure. The implications for material science are just as big. The MgO polymer coating technique is already being studied for use in air purification and even medical blood filtration. Engineering is often about trade-offs, speed versus cost, or power versus efficiency. But every once in a while, a breakthrough like this comes along that breaks the rules. Sungkyunkwan University didn't just build a better filter, they proved that we can harness the energy of our environment to fix the damage we've done to it. It's a reminder that the most complex problems often have elegant, mechanical solutions hidden in the physics of everyday things. Next time you see water flowing from a cap or rushing down a river, think about the hidden energy inside it, and think about the tiny, invisible particles that we're finally learning how to catch. The engineering behind the self-powered nanoplastic filter isn't just about cleaning water. It's about a new way of seeing the world, where every flow is a source of power and every material is a tool for change. Because when we master the mechanics of the invisible, the impossible becomes just another engineering challenge. I'm Awade, and this is how the future works.